Hello everyone, welcome back. In this lecture, we are going to talk about the climate considerations in different design procedures. So far we have been talking a lot about climate and its effect on material properties. So we have seen how material characterization is carried out, right? So we have seen it for granular layers, we have seen it for bituminous layers. What is the effect of climate on those material properties? So we have quantified different climate based parameters. We have solar radiation, rainfall, wind speed, air temperature, many parameters which influence the bituminous layer, and then we have water content which is going to influence the granular layer, right. So we have discussed the effect and the magnitude of this variation on the material properties. Then we looked into the EICM module, which is an enhanced integrated climate module, and how it takes into account of the variations in climate and how it translates into the material property and how these variations are incorporated in the design procedure, right. So in continuation with that, I am going to spend the next few minutes in talking about the consideration of all these variabilities related to climate on material properties and how they are taken into account in different design procedures. So so far we have come across different design procedures. To name a few, we have the IRC 37 design procedure, which is used in India, and we have been commonly referring AASHTOWare design procedure. In AASHTOWare also we have a 1993 version, and then we have a 2004 version which is MEPDG. Then we have AASHTOWARE's design procedure. Then we have South African Pavement Engineering Manual. So we have different design procedures that are available. So we are going to see how to translate the effect of climate on material properties and how it is incorporated in these design procedures. So here we are going to focus on three different softwares which help us to carry out pavement design and the options available in incorporating the material properties. So we are going to focus on different tools. One is IATPave, other one is KenLayer, and the third one is AASHTOWare, right. So we are going to take these three design softwares and see how climate is addressed in each of these softwares. So let us now first look at IATPave. I am sure many of you would be familiar with. Again, I am not going to go through the entire design using IATPave. You will be hearing about it in the subsequent lectures, right. So I am not going to talk about the design procedure using IATPave, but I am going to talk about the options available to input material properties and whether there are any considerations in this particular tool to take into account of the variability in material properties because of the effect of climate, right. So now if we look at the IRC 37 design procedure, which gives guidelines regarding pavement design, we see that this guideline suggests design of pavements using an average annual pavement temperature of 35 degrees Celsius, right. So if there are deviations from this specified temperature, then the design templates which are suggested in IRC 37 have to be re-evaluated, right. So that is the specification with respect to temperature in IRC 37. Now we know that we have bituminous layer and then we have granular layer also, which are present in our pavement. The bituminous layers will be subjected to the influence of temperature. In the previous lectures, we have seen that temperature is the major factor which influences the variation of bituminous layer properties, and this also varies with the age, right. So this we have seen in the previous lectures. So then how do we determine the pavement temperature? Again, what we measure is air temperature. We have to have appropriate correlations to convert air temperature to pavement temperature. Again, we have seen that we are using surrogate models which are developed for other locations and other climatic conditions. If we attempt to use the same for Indian conditions, we have seen the amount of variability also, right. So air temperature to pavement temperature is another concern that we have to address here. Then if we look at the granular layers, we have seen that soil moisture content plays a major role in influencing the modulus value of the granular layers, right. So we determine what is the moisture content present in soil, make appropriate correlations. We have seen soil water characteristic curve. So, we determine the moisture content and the water retention capability of the soil, and then we calculate the appropriate influence on modulus, right. So, the granular layer properties vary with moisture content, right. So, before we move on to the IAT PAVE software, let me show you some data which talks about the variability in temperature distribution for two locations which have identical AAPT values. Let us say that we are comparing Jaipur and New Delhi. The maximum air temperature is 45.8 and 44.3, minimum air temperature values are closer. So, we use these air temperature values in a pavement temperature model and predict the pavement temperature. So, these are the pavement temperature values for these two locations, the maximum pavement temperature, the minimum pavement temperature, and AAPT is also calculated. You can see that the AAPT values are closer, right. So, now if we attempt to plot a distribution of the pavement temperature, right. So, in this study the air temperature data was collected for these two locations for 2 years, and an appropriate pavement temperature model was used to convert the air temperature into pavement temperature, right, and then the pavement temperature value was plotted in terms of a histogram, right. So, the frequency distribution for individual temperatures are seen here. So, for Jaipur we can see that it is mostly concentrated in these temperatures, whereas for New Delhi we see extreme values. We see some values having higher temperatures and some values having lower temperatures as well. These temperature values are going to be critical in terms of rutting, and these values are going to be critical in terms of fatigue cracking, right. So, though both of them have identical AAPT values, the temperature distribution is different. In fact, when the data was analyzed in detail, it was seen that the number of days in which the pavement temperature is greater than 55 degrees Celsius was about 60 in the case of New Delhi, whereas it was around 31 in the case of Jaipur, right. So, this shows that though locations may have identical AAPT values, their frequency distribution is different, and depending upon the frequency distribution of these pavement temperatures, the distress will also vary. So, we have seen that for highways located in these two locations, the distress prediction was also different, right. So, this is the influence of the temperature distribution that we observe in a location and why we should take this into consideration in our design, right. So, now when we move into IAT PAVE, this is the screen that we have to input our values, right. So, we specify the number of layers. You can see that for each layer we have a box wherein we can input our modulus value, right. So, we have a box wherein we can input our elastic modulus, Poisson's ratio and thickness, right. So, there is one value which we can input for layer 1, one value for layer 2 and one value for layer 3. Right. So, this is the only provision available to input the layer modulus, and we do not have any provision to adjust these modulus values depending upon the effect of climatic conditions, right. So, this is with IAT PAVE. Next, I am going to introduce another software to you which many of you may not be quite familiar with. It is called as KEN-Layer. So, this software was proposed by Huang. Right. So, he authored one of the famous books on pavement design. So, he has proposed this software. So, we have 2 modules, KEN-Pave for flexible pavement and KEN-Slabs for rigid pavement, right. So, let me show you what this software has in terms of incorporation of material properties and whether climate related effects can be taken into account in this software. So, this is the main screen of this software, right. So, we have a place wherein we can give input for each layer. So, once you click this layer input, these are the options. So, just for the sake of completeness, let me go through the options. One is type of material. So, we can say whether it is a linear, it is going to exhibit a linear response, non-linear, viscoelastic or combined, but most probably we will be using a linear layered and elastic analysis, but if you want other considerations also we can give in this software. Second is about damage analysis, let me skip this. Third one is number of periods per year which we are interested in. So what this software does is, we will be able to split the design period into different seasons for a given year, right. So maximum we will be able to give up to 12 periods in a given year. So what this software does is, it collects different modulus value for each of these design periods. So if I give period 1, it allocates a proportion of axle loads during period 1, and that particular modulus is used for computation of strains. So like that, for each period the appropriate modulus value is used for design. So by default it is 1, wherein we just use one single value like we had seen before in IRC 37. The maximum that you can give is 12. Sometimes we can also divide it into 4, considering the 4 seasons that we might experience, right. So we can give values anywhere between 1 and 12 for this option. So this is where the variability and material property is going to be taken into account, right. So we have all other parameters, I will skip all of it. I will just show you the material property input window alone. So when you want to give this layer modulus, so you can see here, since we have given only one period in the previous, so in this case we have given number of periods per year as 1. So since we have given it as 1, we are seeing only one tab which is enabled, right. So like I said, maximum is 12. So if you give 12, all these tabs that you see here will be enabled, and we will be able to give material properties, right. So you can see for period 1 we are required to give an input value. So the appropriate values we can give for each layer, right. So if it is a particular month, season 1, we can give the corresponding, we can identify the expected temperature during that period, so the corresponding variation in modulus. Similarly, the expected moisture content in the soil and the corresponding variation in modulus for granular layer. So now if you see here, for layer 1 this is the modulus value, for layer 2 this is the modulus value, right. So I have just given some arbitrary number to illustrate, but we can give the appropriate value for layer 1 and layer 2 depending upon the climatic condition prevalent in that particular season, right. So this is for period number 1. If you have 12 periods, we will have 12 windows like this, and for each period we have to input the layer modulus for each of the layer, right. So this is a slightly advanced slightly better consideration, I would say, over the other design methodologies wherein a single point measurement is used. So at least here we are able to divide the period, divide the calendar year into different seasons, and then take into account of those in design, right. So this is about Ken layer. Next I will talk about AASHTOWare, which is a comprehensive software which takes into account of lot of variables and tries to quantify its effect on material properties. So previously I was discussing about the enhanced integrated climatic model, and I was saying that this module is inbuilt in the AASHTOWare software. So once we give certain input parameters regarding climate, the software appropriately adjusts the modulus of different layers and then uses it for design. Right, so let us see how these values are input in the software and what are the outputs that we get from the EICM. So the inputs required for the climate data file, there is a separate climate database that we have to enter, right. For the locations that are present in US, there is a default list of weather stations. So if you pull down the option there, the stations for which climate database is available will be listed. We can either choose locations from that, or we can upload our own climate database, right. The parameters that will be present in the climate database are air temperature, precipitation, wind speed, relative humidity, percentage of sunshine, groundwater table depth. So we need all these 6 parameters to be input in the climate database, right, and hourly data is required for a period of minimum 2 years. So more details about this we had already seen in the EICM module, right. So then what this EICM does, we have seen that there is a climate material structural model which translates the effect of climate onto the variation in material properties and the structural response that we observe. Then we have a CRREL model which is used for heave and thaw settlement. Again, all this we had seen, and we have an infiltration and drainage model which takes into account of the rainfall that we have observed and converts that into the moisture content that is present in soil, right. So, these are the modules which are present in EICM, which is inbuilt in this particular software, right. So, as a user we will be required to choose the climate database, or we have to upload the climate database, right. If we create one, we have to upload this. So, this is what we have to do as a user. So, all these things are already inbuilt into the software, right. So, once we do this, this is how the database will look like. You can see this is day 1, first hour, the temperature is given, wind speed, sunshine, precipitation, humidity, water table, right. So, this is how the climate database will look like. So, like that we give for 24 hours. You can see here we will be having data of 24 data points before we move on to the second day, which is 2nd of January, right. So, for each hour we have to give all these input parameters. Now, can we create, if I want to use a software like AASHTOWare and carry out pavement design, will I be able to update our climate information into AASHTOWare, right. So, here we have created a climate database for 13 locations in India. So, these are the locations for which we have created the climate database in the appropriate format, collected information about all these parameters from the Indian Meteorological Department, IMD Pune, right. And each of this data was having a lot of missing points and errors. So, all this data was corrected, and there is a template in which it has to be arranged to be uploaded into the software. So, it is arranged in that specific manner and the climate database is ready. So, for India we have for about 13 locations spread across the country. Now, we can use these climate database files if we want to carry out pavement design for India using AASHTOWare, right. So, this consideration of the realistic climate conditions could be done if we want to use AASHTOWare software, right. So, this is again the missing data was filled in by a moving average method, and lot of pre-processing was done before this data was used in the climate file, right. So, this is with regard to the weather data. Now, let us look at how the sublayering is carried out in AASHTOWare. So, what is this sublayering? We might have one particular layer, let us say, so this is given in feet and inches. Just to illustrate, let me stick to the same units which is given in this plot, right. So, the maximum sublayering depth that will be used is 8 feet, right, and each layer will be sublayered in different manner. So, let us say that this is a bedrock, this is a natural subgrade, the next layer is a natural subgrade, then we have a compacted subgrade, then we have unbound subbase lying over it, then we have unbound base, asphalt base and asphalt concrete. So, these are the layers which are present in a pavement, which is taken here for example, right. So, these are the sublayering options. So, for asphalt concrete layer, the top 0.5 inches is one sublayer and the next 0.5 inches is another sublayer, right. After that, it is taken in 1 inch increment till a depth of 4 inch, okay, and 4 inch increment till a depth of 8 inches, and remaining whatever is left is taken as one block, right. So, this is how the asphalt layer is sublayered. Now, why do we have to carry out this sublayering? We can see here, let us say this is maybe 10 inches, let us say this is 10 inches. It is not appropriate to use the same modulus value for all the 10 inches of this particular layer. The top surface will be subjected to high temperatures and thus the modulus will be relatively lower compared to a layer which is present in the bottommost portion. So, if I take the top 0.5 inches, the modulus of this layer is going to be relatively lower than the bottommost 0.5 inch of this asphalt base, right. So, to take into account of this variability and to use the appropriate value rather than using an average value for the whole layer, this sublayering concept is used, right. Similarly for the granular layer also. So whatever is the layer which is close to the water table, that layer will have more moisture content and therefore lesser modulus compared to another layer, right. So like that they have different sublayering options. So if you look at unbound base, it is 2 inches if the thickness of the base layer is greater than 6, and for all others they have an interval in which this is 6 inches. For all other layers they have a manner in which it could be sublayered, right. So like this you can see for unbound base, unbound subbase, compacted subgrade, natural subgrade and all layers, right. So they are sublayered and the sublayer thickness varies from layer to layer. So this sublayer, for each sublayer individual modulus values are assigned, and when the pavement design is carried out, instead of, let us say this is 1, 2, 3, 4, 5, instead of 6 layers, right, all the sublayers will be considered and the pavement design will be carried out. The stresses and strains will be computed for all the individual sublayers, right. So appropriately the modulus value for the sublayers will be taken into account. So for the granular layer, the ratio of monthly to optimum moisture content is used to adjust the resilient modulus. Okay, so from all the soil water characteristics curve and other soil properties, we will be able to get the moisture content that is present in soil. So over the entire month, whatever is the moisture content present in soil, the ratio of that to the optimum moisture content is taken and the resilient modulus is adjusted accordingly, right. So this is the sublayering and the appropriate material property that is used in AASHTOWare. So then how does it take into account of temperature? So we have seen that we have hourly data for each location, right. So for each of this sublayer, the hourly data will be used, right. So the hourly data will be used and it will be converted to, so we have given hourly air temperature, this will be converted to hourly pavement temperature, okay. So this pavement temperature is taken here and it is fitted with the normal distribution, okay. So this is for a monthly data. So this kind of distribution is fit for the data collected for every month, okay. So for this monthly pavement temperature data, a distribution is fit and it is divided into 5 equal portions, each representing 20% of the data. So they are called as temperature quintiles, okay. Now each quintile is taken and one average value is taken for this quintile, because you can see here from here to here the variability in temperature will be very less. So one representative value can be taken for this particular quintile rather than taking it for the entire temperature for that month, right. So the first quintile, one representative temperature value will be taken and that will be used as the material property in calculation of the strains. Then it is done similarly for the second quintile, third quintile and so on. Again this is done for every sublayer which we have seen earlier for the asphalt layer, right. So monthly pavement temperature for a selected year, it is considered to follow a normal distribution and the dynamic modulus is calculated individually for each quintile. So we have an asphalt layer, we have given the temperature and we have given the pavement temperature. The pavement temperature distribution along the depth is also calculated, right. So from that the appropriate dynamic modulus will be calculated for each temperature quintile, right. So this is the consideration of material property and its variability with respect to temperature. So now we can see here for bituminous layer, it is, if you use a level 1 kind of an input, again I will tell you what level 1 is. Level 1 kind of an input is a very precise input which is measured for that particular material which is going to be used in the site, right. So there are no assumptions here, there are no empirical equations which are used to predict the material property. So for bituminous layer at different frequencies, you can see here these are the frequency ranges from 0.01 to 25 hertz for different frequencies and different temperatures. The bituminous layer modulus is measured, right. So this is dynamic modulus So, the dynamic modulus value is measured for different temperatures and frequencies. So, this value is input here and it is used to construct a master curve. So, how does a master curve look like? So, this is how a master curve will look like for a bituminous layer. It is based on time temperature superposition principle. Again, this you should have been briefed about in one of the previous lectures. So, we use this and construct a master curve, right. So, this is how the master curve will look like. It is constructed for a specific reference temperature, but from this master curve we will be able to take modulus value for any given temperature and any given frequency, right. So, this accounts for the variation in pavement temperature and this accounts for variation in vehicle speed, right. It will be taken from the master curve and appropriately the stresses and strains will be computed. So, alternatively for granular layers we have the resilient modulus which are used. So, we have a value for the granular base, granular subbase and subgrade layers, right. So, these are the material properties which will be input into the AASHTOWare software. If we have to use the AASHTOWare software for India, let us say, what are the additional data that has to be collected, right. So, we have seen that there are a number of empirical equations, climate modules which are used in the software. So, all these things have been, the data corresponding to all these things have been collected, calibrated and validated for US conditions, right. So, if we have to use this software in India for computation of the distresses for locations in India, we have to collect additional data or make suitable modifications to the available data. So, what kind of modifications we will be making? The first one is the climate database. So, we have seen that we have climate database for Indian conditions for about 13 locations in India, right. But if we want the climate database for a particular location which is more close to the site at which we are constructing, then we have to have more number of climate databases so that we can be as close as possible. So, this is the first information that we want. The second information is evaluation of EICM model for India. Again, we have seen that all the sub modules, the CMS model or the CRREL model, infiltration drainage model. So, all these models have been developed, calibrated and validated for the climatic conditions prevalent in US. So, we have different correlations, air temperature to pavement temperature, the influence of wind speed on it, the radiation, the amount of radiation falling. So, all of them have been calibrated for US conditions. So, we have to develop similar kind of a model or we have to make suitable amendments to the EICM model to be able to use it for Indian conditions. The third one is dynamic modulus value for different aggregates and binders. Again, if we are using a level 3 kind of input which is more related to the default values available in the software, we do not have the modulus values for the type of mixes that we use in India, right. So, we need to collect more amount of data related to dynamic modulus for different aggregate and binder and then we should be able to use it in the software. Then the measurement of resilient modulus also has to be carried out for granular layers, right. So, only if the resilient modulus value is measured and used, then appropriate modifications to the value can be made to consider the effect of moisture content. And finally, this is the fourth one. So, the final one is related to field rutting and cracking data, right. So, we have constants in the model. So, we have distress prediction equations, right. So, in these distress prediction equations, we have constants like the constants that we have in our rutting, in our NF and NR equations, right. We have similar kind of constants in the distress prediction model in AASHTOWare also. Again, these constants have been calibrated for the specific conditions in US, right. So, if a particular strain is given, what is the corresponding rutting or fatigue cracking or any other distress. Again, we have to calibrate the constants in the model for the conditions present in a given location. So, they have two kind of values which are specified. One is the global calibration factor we also have another calibration factor called local calibration factor. So, this global calibration factor is to take into account of the global variation in mix properties, right, and this local calibration factor takes into account of the variability between laboratory and field data. So, there are 3 local calibration constants and 3 global calibration constants. So, once we identify this for a specific location, then we will be able to more accurately predict the distresses for the selected location, right. So, these are the different parameters or different kinds of information that we have to collect and use it in the AASHTOWare software if we have to use a similar kind of tool for Indian conditions, right. So, this is in an overview about the consideration of the effect of climate on material properties in different design tools, right. So, I thank you for your time here.